Today, we are looking at section 7.1, classification of ordinary differential equations. We will verify the solution of an ordinary differential equation and find the general solution and a particular solution for a differential equation. These are the two things that we're looking at today. So what does an indefinite integral represent? Well, this picture that I have down here is actually pretty helpful for it. If I have a derivative differential equation that is equal to 2x, when we integrate that, we get x squared plus c. So this x squared plus c is that indefinite integral. That represents the entire family of functions that's a parabola. So it could be down here, it could be down here, it could be up here. This entire family of parabolas that open upwards is that picture of what the indefinite integral represents. So this is a family of functions that satisfy the given derivative. That's probably not 100% math correct, but given a derivative, when I integrate it, I get a family of functions. So solving differential equations, a function y equals f of x is called a solution to a differential equation on the interval I if when y and its derivatives are substituted into the equation is satisfied for all x in the interval I. This is where we're going to verify that we have a solution. The general solution of a differential equation represents all the solutions to the differential equation and is in the form of an equation with arbitrary constants. That's your plus c. Any solution of a differential equation obtained from the general solution by assigning values to the arbitrary constants is called a particular solution. So this is when we solve for c. Okay, so here's an example of that, a picture. If I have this differential equation where y prime equals 2x, that's the same idea as this. Here's my general solution with the x squared plus c. And my condition, if I give you an initial condition, and we've already done problems like this, with an x value and a y value, when we put those in, we can solve for c and get 25. So this one's our general solution plus c, and our particular solution has solved for c. So example 1, this word verify here is our clue. Verify that y equals f of x equals x to the fourth minus 5x plus 1 is the solution of the differential equation y double prime minus 12x squared equals 0. So what we're going to do is we're going to substitute into that second derivative. So I have to find a second derivative. So y equals x to the fourth minus 5x plus 1. To get to a second derivative, we know we need the first derivative. And so my second derivative is 12x squared. Great. We're going to start with second derivative minus 12x squared equals 0. So in for that second derivative, here's our 12x squared minus 12x squared. This is that original equation. Does that indeed equal 0? So 0 equals 0. That's true. We verified. So you don't have to solve anything for these. If they say verify, it's like I gave you the answer and you just want to make sure that it's true. So example B is the exact same idea. We've just switched out the constants, the -5 and the 1 for these generic terms, C1 and C2. So we'll do the same thing. I know that y is equal to x to the fourth plus c1x plus c2. The first derivative is going to be 4x squared plus c1. And the second derivative, nope, that's a cube, is 12x squared. So what we need to do is take that original equation again. Second derivative minus 12x squared equals 0. In for that second derivative, we'll put 12x squared minus this original piece. And again, 0 equals 0. So we verified that it's true. Done. All right. So a boundary condition or an initial condition is a restriction on the variables of the general solution that leads to a particular solution. So what we're really doing is giving values that allow us to solve for C. So generally it's an X and a Y. They could be other variables, but generally it's the X and the Y. So example 2, find the particular solution for dy over dx equals 6x squared plus 5 with an initial condition of x equals 1 and y equals 10. So I'm going to say, I'm going to rewrite the problem, dy over dx equals 6x squared plus 5. I'm going to show you a little something that we'll do in the next lesson. I hope it helps. So we integrate both sides. Our goal is to get a y equals equation. That's our goal. We want a function. Now, before we integrate, we have to have a dx over here.
Not yet.
How do we get a dx over there? Well, we multiply. So we're going to take this dx, we're going to multiply on both sides, and when we do, it winds up over here, which is perfect.
Okay.
So now I have only y terms on the left and only x terms on the right. So now we integrate. So the antiderivative of dy is going to be y. 6x squared becomes 6x cubed over 3 plus 5x plus c. I'm going to simplify the 6 over 3. So I've got 2x cubed plus 5x plus c. And now we have that initial condition. We know that x is equal to 1 and y is equal to 10. So even if I didn't tell you what to do, your instincts would tell you what to do. So you're going to put 1 in for x and 10 in for y. So this is 10. Here's a 1 cubed. Here's a 1. These are looking like holiday colors here. So this is 10 equals 2 plus 5 plus c. When we combine like terms and put it all together, I get 3 equals c. Now, the algebra student in us wants to box this as our answer and say, hey, that's it, we have the solution. Remember, I want a y equals equation. So you have to rewrite the equation with the c in there. You're going to tell me y equals 2x cubed plus 5x plus 3. This is your final answer. Find the particular solution, which means we have solved for c. Awesome. Example 2. Example 3 is going to work exactly the same way. Find the particular solution, which means solve for c, for dy over dx equals e to the x for sine of 2x with an initial condition of x equals 0 and y equals 4. So let me start by rewriting the problem. I know that if I multiply both sides by dx, I'll write it out this time instead of showing it moved. These cancel. So we're going to integrate dy e to the x plus 4 sine of 2x dx. So on the left, if I integrate dy, this becomes y. The antiderivative of e to the x is e to the x. The antiderivative of 4 sine of 2x. Technically, this is a chain rule, and I'll write it out, but I know that some of you can do this in your head. So u is equal to 2x. du is equal to 2 dx. So I know that dx is equal to du over 2. So this will be, if I write this out over here on the side, 4 sine of u in place of dx, I'm going to put du over 2. Du over 2, the 4 over the 2 becomes 2 integral of sine of u. The antiderivative of sine is negative cosine. Negative 2 cosine of u, and then I'll replace this u with the 2x when I rewrite it. Let me scooch these out of the way. There we go. So this becomes minus 2 cosine. I'm going to replace that u with a 2x plus c. But I want the particular solution, so I need to replace x and y with the 0 and the 4. So y is going to be 4. The x is 0. This x is 0. So 4 equals e to the 0 minus 2 cosine of 2 times 0 plus c. Watch that 0. I know a lot of times we try to make it be a 0, but in this case, e to the 0 is 1. So 4 equals 1. 2, the cosine of 0 is really 1 plus c. So 4 equals 1 minus 2 plus c. That's a negative 1. 5 equals c. So again, 5 equals c is not your final answer. You need the whole thing. Y equals e to the x minus 2 cosine. Let me redo this.
I am, I'm showing everybody your stuff. Did you?
Y equals e to the x minus 2 cosine of 2x plus 5. There you go. That's the final solution. This should be a pretty straightforward assignment. Let me know if you have any questions. Good luck.